Still talking about derivatives here. This is looking at computing derivatives numerically using values. Um, I'll show you a calculator function here. If you have some kind of a function that looks like this, this expression is for the slope between 2 points, right? When we're, that's something you learned in grade 10. What we've been doing here, talking about the derivative, is looking at the limit of this as h approaches 0. The calculator can approximate derivatives at a point, and you can do the same thing. You can approximate derivatives at a point. I think I may have told you this before, but I had a student who came back and said, "Oh, I'm really struggling in calculus. I wish I had taken it at high school." And his coping strategy sometimes, actually, it's pretty, like, he's a smart guy. I mean, this is a way of checking his answer for things, is if he was trying to find the derivative here, what he would do is, if he wanted the derivative at 2 for a function, he would just find the slope between 1.99 and 2.01, because it's going to be pretty close, right? If he picked 2 points that were really close together and found the slope, so if he was supposed to find the derivative here, the actual value, he just picked a point there and a point there, and that line is going to be pretty close to the line he wants. Does that make sense to you? That's what the calculator does when you ask it to approximate a derivative. And there's two things it could do. If it wanted the derivative at a certain point, like if it wanted the derivative at that green point there, we'll expand this a bit here. If it wanted the derivative at the green point, we'll make this is farther away, right? So if it wants the derivative here, what it could do is say a point on the left, a point on the right, and do the slope. Or it could just do one side or the other, right? It could put a point on one side and a point on the actual point and do that. Or it could do one on the other side, make h negative, right? The one we've used to come up with the derivative is this one-sided quotient. If we want the derivative at 2, we've put a point at, we've put a point at 2, and we put a point at 2 plus h, and then we've moved this closer to 2, right? We've made h become 0. We could have done it this way and said, if we want the derivative at 2, we could do the slope between 2 plus h and 2 minus h, right? You could do the slope between those two and then just have them both collapse on the point in the middle. All right? This is what this is. These are going to have the same limits as h becomes 0. Let me pause. All right, so what I'm saying here is, if you want the derivative at that point, as in you want the slope of that red line, we could approximate it. Like, your calculator is not programmed to do limits and work with algebra and stuff like that. Your calculator, or if you want to just approximate it, if all you have is a table of values, you can approximate the slope of the red line by just finding the slope between 2 points and just making them really close together, right? You can make the distance in between them small enough that, like, if you made the distance in between them 1, they're pretty close, right? I mean, as long as you get the points close enough, the slope is almost the same, right? You could go on either side and it wouldn't matter whether you make h positive or negative. If you make it too far away, it's not going to be a good approximation. Or you could do this and you could make it symmetric. You could go a plus h and a minus h, right? And then you could make the slope, the distance in between really small. Actually, this, for a lot of functions that are nice and smooth and continuous and aren't all zigzag and choppy, this is actually a pretty good approximation, even if h isn't that big. Like, look how far away h is there, and it's still, that green line looks about the same slope as the red line. It's not exactly the same, but it's a pretty good approximation. So certainly if you made h small, it's a really good approximation. If you're not taking the limit, making it symmetric on either side, a plus h, a minus h, is better than this. If you are taking the limit, they all have the same limit. If we put them both there, if we make this smaller and smaller, and the smallest I can make it is 0.1 on here, they all kind of converge on the same thing. If you're not going to take the limit, which one of those lines is a better approximation of the red one? The green one, right? This is a better approximation of the red one. If you're not doing the limit, if you're programming a calculator to approximate derivatives, it's probably better to use the symmetric difference quotient, as in pick a point above, and pick a point below. okay? Because that's going to be a better approximation than that if you're not actually taking the limit. So why I'm showing you that is I'll show you the calculator function, and that's essentially how it works. Okay, it works on basically what I told you the former student did is if you want the derivative at 2, it just says let's find a function value at 2.01, let's find a function value at 1.99, and then just calculate that slope, and it's a good approximation. If we want the derivative here, if you were finding the derivative from the definition of the derivative, you'd say limit as h approaches 0 and all that stuff, right? The calculator is not programmed to analyze the thing algebraically. All it does is it says, if I want this derivative, so f prime, if this is called, if f of x is x cubed, just so we can use some shorthand here, f of x is that function. F prime at 2 is just the slope between points that are really close to 2. So on the bottom here, if I pick well, let's actually do a really crude approximation. Let's do the slope between 3 and 1. All right, so here's x cubed. If we want the derivative at 2, we can approximate it by doing the slope between 1 and 3. What are the y values for that? If that's our function. 1 cubed is 1, and 3 cubed? No, cubed is 27, is that right? So we want the difference between there. If we want to approximate the slope here, we're going to do it by, a really rough estimate would be using those 2 points. So you can say it's f at 3 minus f at 1, right? Or in other words, 27 minus 1 over 3 minus 1. So what is that? 26 over 2, 13. If you wanted a better approximation, and I should actually say, this should say roughly equal to here, right? If you want a better approximation of that, you use points that are closer to 2, right? So you might use 2.1 or 2.01 minus 1.99. Pick points that are really close to that. And then you need f of 2.01 and f of 1.99. So in other words, you do those cubed, work that out. Can you work this one out using your calculator? I'm going to pause this while you... A really rough estimate of the slope at 2 would be to say, let's just look at a point at 1 and a point at 3. So on the bottom, the slope is 3 minus 1, 2, right? On the top, it's whatever this is, 27 minus 1, 26. So you're just approximating that. A better estimate would be to make this smaller, right? So the one I just suggested to you, actually I can't do on here. Oh, I can actually. I could just make this down to 0.01. That's actually going to give you a really close estimate of that. If I can manage to make it stop on the right thing. That's going to give you a really close estimate because it's almost collapsed on top of it there. I don't have the slope displayed here, but that's what you're doing, right? If you want an approximation of a derivative, you can just pick points that are really close. What does this work out to if you did the slope here? If you did 12 point something? How many zeros? 3 zeros and a 1. If you made this wanted to make it even better, you could make this 2.000. You could make it really close and it would be able to calculate it. If you do this, I think you find if you use points that are close enough, it's roughly 12. Okay?